Welcome to our deep dive, and this time we're going to try to wrap our heads around quantum approaches to consciousness.
A perfect topic for our philosopher listeners.
They've probably spent years, maybe even decades, pondering the mind-body problem, right?
Yeah.
But we're going to throw quantum theory into the mix just to make things even more interesting.
Yeah, it's going to be fun.
So, to guide our exploration, we'll be drawing wisdom from the Stanford Encyclopedia of Philosophy. And they kick things off with this pretty thought-provoking statement. It is widely accepted that consciousness, or more generally, mental activity, is in some way correlated to the behavior of the material brain. Since quantum theory is the most fundamental theory of matter that is currently available, it is a legitimate question to ask whether quantum theory can help us understand consciousness.
It's like we have this incredibly powerful tool in quantum mechanics describing the universe at its most fundamental level. And then we have this huge mystery of consciousness that we're still trying to crack.
Right.
It's just natural to wonder if they might be connected somehow.
Absolutely. And the Stanford Encyclopedia outlines three basic ways this connection might actually play out. They call them quantum brain, quantum mind, and dual aspect. But before we get lost in the quantum weeds, maybe it's a good idea to kind of step back and map out the philosophical territory, right?
Absolutely, and I think our philosopher listeners will appreciate that.
Yeah.
So first off, it's important to understand the difference between descriptive approaches and explanatory approaches to consciousness. Descriptive approaches, they focus on correlations. For example, we can see which brain areas light up during certain mental states, but that doesn't necessarily tell us why those correlations exist.
Oh, I see. So it's like saying, hey, ice cream sales go up when the temperature rises.
Yeah.
That's a correlation, but it doesn't really explain the underlying cause, which is that people want to cool down on a hot day.
Exactly. So explanatory approaches, on the other hand, they actually look for those underlying causes, the mechanisms that explain why the mind and brain are connected. And here's where things get philosophically really, really interesting. Even in physics, we have boundary conditions, like the initial state of the universe, which aren't explained by the fundamental laws themselves.
Oh, that's a good point. So even in the most fundamental sciences, there are always deeper questions lurking beneath the surface.
Absolutely. Now, let's think about how the mind and matter might connect. There are two basic models to consider.
Okay.
And both of them have, huge implications for how we understand consciousness. The first one, what we'll call Model A, this is the direct approach, says that mental states and brain states directly interact.
So like my thought about wanting pizza directly causes certain neurons in my brain to fire.
Yes.
And then leads to me, actually ordering pizza.
Exactly.
Okay.
Now, Model B, which is the indirect approach, it proposes something a bit more radical. It suggests that there's a third neutral category from which both mind and matter emerge.
Okay, so it's not that my thoughts are directly causing brain activity, but rather that both thoughts and brain activity are arising from some deeper, more fundamental level of reality.
That's the idea. And this takes us into some familiar philosophical territory, right? Things like reductionism, trying to explain everything in terms of its smallest parts. And then emergence, the idea that the whole is more than the sum of its parts. And of course, the hard problem of subjective experience, that question of how physical processes in the brain give rise to the feeling of what it's like to experience something.
Ah, yes, the explanatory gap.
Exactly. I'm sure these are all concepts that, as a philosopher, you've wrestled with before.
Oh, absolutely. Reductionism versus emergence, the nature of qualia. These are kind of central to my philosophical work.
And that's exactly why I think you'll find these quantum approaches so fascinating. They offer a new lens to examine these age-old philosophical questions.
Okay, you've definitely piqued my curiosity.
Right.
So let's start with that first category, quantum brain. What are some of the specific attempts to apply quantum theory to the brain itself?
Well, the proposals out there range from very concrete ideas to some that are pretty wildly speculative.
Okay.
And, it's important to point out that some accounts just kind of throw around quantum buzzwords without any real substance.
Sure.
So we're going to focus on those approaches that have some, genuine scientific effort behind them.
Okay, sounds good.
Now, to help organize all of this, let's think about the brain at 3 neurophysiological levels.
Okay.
First, we've got the neuronal assemblies, those huge networks of neurons.
Right.
Then we can zoom into the level of individual neurons and their connections, the synapses. And finally, we get down to these incredibly tiny structures within neurons called microtubules.
Microtubules. Wow, that's getting down to the, subcellular level. Is that where things get really quantum?
We'll see.
Yeah.
So, are you ready to meet some of the key figures in this field?
I am. Let's hear what these quantum brain explorers have come up with.
All right. Okay, so let's start with Henry Stapp.
Okay.
He's a physicist who's been exploring this quantum mind connection for decades.
Wow.
And his work really centers around this idea of the role of observation in quantum mechanics and how that might tie into consciousness.
Okay, now hold on a second. Observation in quantum mechanics. Could you remind me how that works
Sure.
and what it has to do with consciousness?
Right. So in quantum mechanics, particles can exist in these kind of fuzzy states called superpositions,
Okay.
where they're sort of in multiple states at once. It's not until we observe them that the superposition collapses and the particle settles into a single definite state.
Right.
So Stapp suggests that this collapse is actually happening in the brain itself.
In the brain. Okay.
And crucially, that our conscious awareness actually plays a role in this process.
So you're saying my conscious act of observing something actually causes a change in the physical world,
That's the idea.
specifically in my brain.
That's pretty radical. It is radical. And it places Stapp firmly in that direct mind-matter interaction camp, our Model A.
Okay.
He even goes so far as to suggest that our conscious intentions could actually influence which quantum states collapse.
So like a kind of quantum free will.
Exactly. Quantum free will.
That's a whole other can of worms.
Yeah.
But okay, going back to the brain for a sec, how does Stapp connect these quantum events, happening at the neuronal level to the large-scale coordinated brain activity that we associate with consciousness? It seems like a pretty big leap.
Yeah, that's a great point. And that's one of the main challenges for Stapp's approach, right?
Yeah.
It's really hard to see how these microscopic quantum events could have such macroscopic effects. And another thing to keep in mind is that Stapp proposes what he calls a hybrid ontology, where consciousness and matter are interwoven in a way that almost resembles a dual aspect framework.
Ooh, as a philosopher, I find that idea particularly intriguing.
Yeah.
It resonates with my own leanings towards kind of frameworks that don't try to reduce consciousness to purely physical processes.
It's definitely a rich area for philosophical exploration. Now let's shift gears a bit. Let's look at a different quantum brain approach. Vitiello and Freeman, these guys, instead of focusing on individual neurons, they use quantum field theory to describe brain states, especially memory.
Quantum field theory, that sounds even more complex.
Right.
How does that even apply to something like memory?
It is a bit more abstract, but stick with me.
Okay.
They propose that memory states are actually like vacuum states in quantum fields.
Okay.
It's almost like thinking of the brain as this vast, interconnected ocean of quantum fields, and memories are like ripples or waves propagating through that ocean.
Okay, so I can kind of picture that. But what are the vacuum states in this context? Aren't they supposed to be empty? How can something empty store information?
That's where it gets really interesting. In quantum field theory, even seemingly empty space, the vacuum, it's actually buzzing with potential energy and fluctuations. It's not truly empty in the classical sense.
Oh, okay.
So Vitiello and Freeman suggest that these vacuum states, despite being the lowest energy states, they actually have this really rich structure that's capable of encoding information.
So our memories are like patterns embedded in the very fabric of this quantum vacuum.
That's the idea, yeah.
That's wild.
It is. It's a mind-bending concept.
It is.
And to explain how we can have so many distinct memories, they use this concept called inequivalent representations.
Inequivalent representations. That rings a bell from quantum mechanics, but I'm a little fuzzy on the details.
Think of it this way. You have a memory of your first bike ride.
Okay.
That memory can be triggered by, seeing a bike or smelling fresh-cut grass or even hearing a certain song. Each trigger kind of accesses the same core memory, but it offers a slightly different perspective on it.
Okay.
So that's kind of what inequivalent representations are like.
Okay.
Different ways of accessing the same underlying state.
Ah, that's much clearer.
Yeah.
So different memories aren't necessarily stored in different physical locations in the brain, but rather as different patterns of activity within this quantum field.
Exactly.
Good.
And this model fits nicely into the indirect approach, our model B,
Right.
because it focuses on the overall dynamics of the brain
Yeah.
rather than specific neural activity directly corresponding to mental states. It's a more holistic view.
Right. It's not about pinpointing, like this neuron is firing because you're thinking about pizza.
Exactly.
It's more about the overall organization of the system.
Yeah.
It's a bit more like an orchestra, where the individual instruments contribute to the overall symphony.
That's a great analogy. Now, ready to zoom back in and explore quantum mechanics at the level of the synapse.
Let's do it. Let's get down to the microscopic level again.
Okay, so this next one is Beck and Eccles and Later Refinements by John Joe McFadden.
Okay.
They focus on that tiny gap between neurons where signals are transmitted, the synapse, and they argue that quantum processes are actually essential for the release of neurotransmitters. Those chemical messengers that allow neurons to talk to each other.
Oh, okay. So they're proposing that even the basic communication between neurons relies on quantum mechanics. How does that work?
They propose that quantum tunneling, this is where particles can pass through barriers that classical physics would say are impassable, plays a crucial role. So imagine a neurotransmitter molecule needing to jump across that synaptic gap.
Right.
Quantum tunneling would allow it to do that, even if it didn't have enough energy to do so classically.
So it's like the neurotransmitter is teleporting across the synapse?
Kind of, yeah.
That's amazing.
It is.
But isn't this idea of quantum effects at single synapses also facing that scaling up problem?
Yeah.
Like, how do we go from these tiny quantum events to large-scale consciousness?
Yeah, you're right. That's a valid point. And it's one that's been raised as a criticism, right? Just like with Stapp's approach, it's not really clear how these faint quantum whispers at the synapse could actually translate into the roar of conscious experience.
It seems like a recurring theme in these quantum brain approaches, bridging that gap between the micro and the macro.
Yeah,
It's proving to be a big challenge.
it is. But this approach has a really interesting link to a familiar experience.
Okay.
Anesthesia.
Oh, okay.
Beck and Eccles argue that anesthetics, the drugs that disrupt consciousness, they actually work by interfering with these quantum tunneling processes at the synapse.
So in a way, anesthesia is like a quantum off switch for consciousness.
That's the idea, yeah.
That's fascinating.
And similar to STEP, this model falls into that direct mind-matter interaction category, Model A. They suggest that conscious intentions could actually influence the probability of these quantum tunneling events at the synapse, again hinting at a quantum basis for free will.
Okay, so quantum free will is back.
It keeps coming back.
It does keep coming back.
Yeah.
But didn't you mention that John Joe McFadden added a twist to this model?
You have a great memory, yes. McFadden, he built on Beck and Eccles' work, and he suggests that consciousness doesn't arise from these individual quantum events at the synapse,
Right.
but rather from the electromagnetic field generated by the collective activity of billions of neurons firing.
Oh, okay.
He argues that this electromagnetic field is influenced by quantum processes, and that it's the global state of this field that gives rise to conscious experience.
So it's not the individual quantum events themselves, but the overall pattern of electromagnetic activity that's shaped by quantum mechanics.
Precisely.
That seems to sidestep the scaling up problem a bit.
Exactly. McFadden's approach really focuses on those holistic, emergent properties of the brain's electromagnetic field, which aligns more with the indirect approach, Model B. He even proposes that this electromagnetic field could interact non-locally, allowing for instantaneous communication between different parts of the brain.
Non-local interactions. That sounds like quantum entanglement might be playing a role here.
You got it. McFadden's model brings in that fascinating concept of entanglement to try to explain how the brain can achieve the kind of coordinated, integrated activity that we associate with consciousness.
Okay, this is getting really interesting. We've gone from individual neurons to the brain's overall electromagnetic field. What's next on our quantum journey?
Right, so we've explored that intricate world of quantum brain approaches, focusing on those quantum processes happening within the brain itself. But now, get ready for a pretty mind-expanding shift in perspective as we dive into quantum mind.
Ooh, quantum mind. Okay, what's the difference?
Well, what's really fascinating about quantum mind is that it doesn't actually require a quantum brain. It's more about how we can use those, strange and counterintuitive concepts of quantum mechanics to understand the mind directly, even if the underlying brain activity is perfectly classical.
So it's not about finding actual quantum events happening in the brain. It's more about using quantum mechanics as a powerful analogy or a metaphor to understand how the mind works.
Exactly. It's like using the mathematical tools of quantum mechanics to create models of mental phenomena without assuming that those phenomena are literally happening at the quantum level.
As a philosopher, I have to say that's kind of appealing to me.
Yeah.
I'm always a bit wary of explanations that try to reduce the richness of conscious experience to purely physical processes. It always feels like something's getting lost in translation.
I get it. And that's where quantum mind offers a refreshing alternative, right?
Yeah.
It acknowledges that mental experience has its own unique qualities that might be best understood using tools that go beyond classical physics.
Okay, so what are some of the specific mental phenomena that have been modeled using this quantum mind approach?
Well, one area where this has been applied is in decision making. Remember how we talked about quantum superposition and probability amplitudes?
Mm.
Well, those concepts have actually been used to model how people make decisions.
Oh,
And
yeah.
surprisingly, these quantum models can account for some puzzling effects that classical models struggle to explain.
So you're saying our decision-making process might be secretly quantum.
Let's just say it's more complex than traditional models suggest. For example, there are these things called the conjunction and disjunction fallacies.
Okay.
These are situations where people actually violate the basic rules of probability when making choices.
Interesting.
And classical models have a really hard time explaining why this happens.
Yeah, that makes sense.
But quantum models, by incorporating ideas like superposition and interference, can actually make sense of these seemingly irrational behaviors.
So our minds might be playing by a different set of rules than we initially thought, rules that are more in line with quantum mechanics.
That's the intriguing possibility that quantum mind researchers are exploring. And it's not just decisions. Order effects, the fact that the order in which we're presented with information can influence our judgments and perceptions, these have also been modeled using quantum concepts like contextuality.
Oh, I've definitely experienced that myself. The way a question is phrased or the information that came before it can completely change my interpretation.
Exactly. And what's really remarkable is that quantum models can account for these order effects with fewer assumptions than classical models.
So more explanatory power with less theoretical baggage.
You got it.
I like the sound of that.
It's like they provide a more elegant and parsimonious explanation. What other mental phenomena have been explored through this lens?
Well, another fascinating area is bistable perception. These are those visual illusions where you can see two different images in the same picture, like the classic Necker cube or the vase faces illusion. Researchers have actually modeled this using a quantum-inspired approach.
So it's like our perception is in a superposition of two different states.
Yeah. And it collapses into one or the other depending on some kind of quantum measurement-like process.
That's the basic idea. And what's really cool is that this model, it's called the Necker-Zeno model. It makes specific predictions about the timing of these perceptual switches. And those predictions have actually been borne out in experiments.
Wow, so there's actual empirical support for this quantum model of perception. That's pretty compelling.
It is. And it raises some really profound questions about the nature of time and consciousness. You see, the model suggests that our experience of time might not be as straightforward as we think. It introduces this idea of temporally non-local mental states where our conscious experience isn't confined to a single point in time.
Temporally non-local. That's a mind-bending concept. It's like conscious experience is somehow spread out or smeared across time.
Exactly. And it gets even weirder. The model actually predicts that it might be possible to test something called temporal Bell inequalities in beastable perception experiments.
Bell inequalities. Didn't we talk about those in the context of quantum entanglement? How could they apply to something like visual perception?
I know, right? That's the mind-blowing part. If these temporal Bell inequalities were violated in a perceptual experiment, it would strongly suggest that something akin to quantum entanglement is happening within our own minds. It would be a pretty radical departure from classical models of cognition.
Okay, my mind is officially blown. So quantum mind isn't just about finding cute analogies, it's actually generating testable predictions and pushing the boundaries of how we understand the mind.
Exactly.
What other areas have been explored using this approach?
Well, researchers have applied it to learning processes, where the order in which we learn things can actually affect our ability to recall them.
Okay.
And this hints at a kind of non-commutativity in cognitive processes, similar to how the order of operations matters in quantum mechanics.
It's like how in math, 2 plus 3 is the same as 3 plus 2, but in quantum mechanics, the order you do things can make a huge difference.
Precisely. And quantum mind is also being used to model semantic networks, which aim to understand how meaning is represented in language. It suggests that the meaning of combined concepts isn't simply the sum of their parts, but something more akin to an entangled state.
So just like entangled particles, the meaning of words is somehow interconnected in a way that classical models can't quite capture.
Exactly, like the whole is greater than the sum of its
Right.
parts. And then there's this fascinating concept of quantum agency, which attempts to use quantum models to explain how we develop a sense of free will and intentionality. It all ties back to, your philosophical interests in the nature of the self and conscious experience.
Quantum agency. That's definitely a concept I'll be chewing on for a while. It seems like these quantum mind approaches are raising more questions than answers, but in a good way. They're really pushing us to think differently about the mind.
That's the beauty of it. And here's one final mind-boggling finding to leave you with. Some researchers have found correlations in psychological experiments that are even stronger than those allowed by quantum theory. They call them super quantum correlations.
Super quantum correlations. So our minds are even weirder than quantum mechanics can account for. I'm not sure if I should be excited or terrified by that prospect.
I think a healthy dose of both is appropriate. It's still early days in this research, but it's clear that quantum mind is a rich and fertile ground for exploring the mysteries of consciousness.
This deep dive has been incredible. We've gone from the subcellular level of microtubules to the mind-bending world of quantum field and entanglement. It seems like the connection between quantum mechanics and consciousness is still very much an open question.
It absolutely is. We've only just scratched the surface. But what's exciting is that these quantum approaches are forcing us to rethink our fundamental assumptions about the mind, the brain, and reality itself. Where do you see the most potential for future breakthroughs? And what philosophical questions does this all raise for you? That's something to ponder.